Let's take a look at this Euclidean geometry question. We've been given a diagram with some information, and they've given us some questions. Question reads, calculate, giving reasons, the size of MOL. Now MOL is this angle right here. That is an angle at the center, and so we should be looking for angle at the center theorem. We know that the angle at the center of a circle is equal to 2 times the angle at the circumference. So the angle at the circumference was given to us as 50 degrees, which means that the angle at the center will be 100 degrees. Next, they want us to calculate L1. L1 is this angle right here. It falls within this triangle right here, which is going to be an isosceles triangle, because since O is the center, OM and OL are equal since they are radii. So we can solve for L1. So L1 is going to be 40 degrees. M2 will also be 40 degrees, and we can verify this because if we add all the angles up, we get 180. Last question is to calculate angle N. Now to calculate angle N, since angle N lies outside of my circle, I can't really use any circle theorems. However, angle N falls within a triangle, this triangle right here. Now if we can figure out the angles in that triangle, then we can work out angle N. Now I see chord KL drawn for me, and I can see that KJ is equal to JL. This brings me back to a theorem where if you have a line drawn from the center, and if it bisects a chord, it means that it's going to be perpendicular to the chord. So now we have 2 angles, and we can figure out the third angle being angle N. So this is my triangle right here. We have an angle 50 degrees. We have an angle 90 degrees. That means we can solve for this angle, which is going to be 40 degrees. Let's take a look at this next question, which reads, in the diagram below, O is the center of the circle, P, S, R, and K are points on the circle, SOK is a straight line intersecting PR at T, PS equals SR, and OR is joined, S1 equals X. The question reads, calculate P in terms of X. So to solve this, I'm going to start by drawing just these lines here that represents the radii. Now, since OR and SR are radii, they are equal in length, which means that this triangle is going to be an isosceles triangle. That makes R1 X. Now we can use some angles in the triangle to solve for O1. O1 will be 180 minus 2x. Now angle P is going to be the angle at the circumference. And we know that the angle at the center is double the angle at the circumference. So angle P is going to be half of 180 minus 2x, which is 90 minus x. Next question, prove that S2 is equal to S1. Now to do that, I'm just going to clear up some space here, and I want to focus on the larger triangle, being this triangle right here. Now this triangle is also an isosceles triangle because they've told us that PS is equal to SR, which means that this entire angle here, R1 and R2, will also be 90 minus x. Now we can use some angles in the triangle to solve for S2. And if S2 is x, then we've proven that S1 is equal to S2. So let's do that. So we'll start by saying that S2 plus S1, which is x, plus 90 minus x plus 90 minus x equals 180, because that's a triangle. So S2 plus x plus 180 minus 2x equals 180. The 180 will cancel. S2 minus x equals 0. That means S2 is equal to x. And therefore, we've shown that S1 is equal to S2. Question 9.2 reads, in the diagram below, O is the center of the circle. A, B, C, and D lie on the circle. BOD is perpendicular to AC. At E, AO and BC are drawn. Prove that 2AO minus ED all squared is equal to BC squared minus AE squared. All right, so let's start with BC. So this triangle right here. And using the theorem of Pythagoras, we can say that BC squared is equal to EC squared plus, and it's going to be BE squared. But instead of BE squared, I'm going to instead write BD minus ED. So BD minus ED all squared. Now BD represents the diameter, okay? And we know that the diameter is double the radius, and the radius is OA or AO. So instead of writing BD, I can write 2AO. So BC squared is equal to EC squared plus 2AO minus ED all squared. So we've got our BC squared, we've got our bracket here, and all that's missing is AE. Now the next thing is that since OE is a line that is drawn from the center and AC represents a chord, and we are shown that it's perpendicular, it means that that chord is going to be bisected, meaning that AE is going to equal EC. So we can replace EC with AE. So our equation is now BC squared is equal to AE squared plus bracket 2AO minus ED all squared. Let's just rearrange this now. So BC squared minus AE squared is equal to bracket 2AO minus ED all squared. Finally, let's take a look at question 10.2. There's a whole lot of information here. Please pause the video and read through it. And let's take a look at the questions. Question 10.2.1 reads, prove that AC is perpendicular to DB. Now, we've been told that BC is a diameter of a small circle. So this line right here is the diameter. So since it's a diameter, it means that this angle right here is going to be 90 degrees. So since it's 90 degrees, it means that those lines are going to be perpendicular. Okay? Moving on, 10.2.2. Prove that AC is parallel to DP. Now to prove that AC is parallel to DP, we're going to first start with this tangent right here. That tangent makes an angle with these chords. So chord FB and chord DB. Those chords subtend two angles, angle C3 and angle P. So it means that angle C3 is going to equal angle P. So let's call this angle X. That's going to be angle X, and that right there is going to be angle X. And if we look closely, now we have the shape of an F, which tells us corresponding angles, which then implies that those lines are parallel. 10.2.3, prove that ABCD is a cyclic quadrilateral. To prove that ABCD is a cyclic quadrilateral, so this shape right here, what we'll do is we'll start with this tangent lines. AD and AB are tangents that originate from the same point, meaning that they are equal in length. That means that D1 is going to equal angle X. Next, we can use the converse of the angle in the same segment theorem to then prove that ABCD is a cyclic quadrilateral. Done. Next question, prove that CP is equal to CD. Now, to prove that CP is equal to CD, we need to show that C3 is equal to X. Now, how can we do that? Now, since we've shown that ABCD is a cyclic quadrilateral, we can do the following. Here's my chord, or segment, if you will. Means that this angle right here is going to equal this angle right here. So since that's X, C2 is also going to equal X. Right? So C2 will equal X as well. And since we've shown earlier that this line is parallel to this line, we can use alternate angles to then show that D3 is going to equal X as well. And now that we've shown that it's equal to X, it means that this triangle right here is isosceles, meaning that CD is equal to CP. And the last question, 10.2.5, prove that BR is parallel to AD. Now, BR is this line right here, and AD is this line right here. Now, how can we prove this? Let's take a look. So first thing we'll do is we'll make a note that since CB is my diameter, we know that this is going to be 90 degrees. But this angle right here is also going to be 90 degrees. Next, we know that since CB is a diameter and AB is a tangent, this angle right here is going to be 90 degrees. This B1 and B2 angle is going to be 90 degrees, right? And next point, since ABCD is a cyclic quad, opposite angles in a cyclic quad are supplementary, meaning they add up to 180. So it means that this angle right here must be 90 degrees as well. And now we've shown that this right here would make them parallel since you have co-interior angles. Okay? That's it. Thanks for watching. Hope you found it useful. I'll see you in the next one. Bye.